And other one thing I should have said this morning when I introduced myself, if at some point you want to discuss about education or teaching, if it's something you're interested in, whether in HPC or not in HPC, that's not the issue. I'm always interested in talking about education and psychology, cognitive processes and all that. So in case that's something you have your eyes on, feel free to come to me anytime. Simon, all good? Perfect. So getting back to the single and master thread exercise. For a change, I'm going to get back to the Fortran version of the code. Okay, don't worry, it doesn't change anything because all you need to do is just the basic conversion between the two. Okay, they have the same structures, they have the same everything. Okay, so sorry for the red indentations here. So the master thread there, how do I wrap this and making sure it's executed only on the master thread? You can give the C code if you have the C code, it's fine. How did you do it? Okay, so you said Pragma OMP, the first one, which one was it? Okay, you want to put parallel first, that's smart. That was my sneaky thing. So you spoiled my sneaky thing right away. Okay, that's fine. I'll forgive you one day. Do you put that after the declarations of the integers or before? Well, we're in Fortran, so we don't have the choice. Okay. Yeah, but in C, yeah. So, OMP parallel. Okay. So I'm going to move all this. So did you close your parallel here? No? At the very end? Okay, that's smart. You really intend to dodge all my traps? OMP and parallel. Okay, so now I would like to execute this on the master thread. OMP master. I move that. Okay. By the way, yeah, that was the sneaky part, because if you were doing master without parallel, then the master thread will also do the other part. But I designed it to have the thread doing the first part being unable to do the second one at the same time if you have multiple threads. Because the master thread will be busy for 1 second doing this useless loop, but still, it artificially blocks it for a second. So if you have 2 threads, if you see that it's the same thread doing both, you know there's something wrong somewhere. Because within a second, the other thread should have plenty of time to start the other part. So, okay, and how do I get the second part in OpenMP? Which construct did you use? Which directive? Exactly. No, Fortran. Oh, careful here. Let's see if it's happy. It seems to be happy. Oh, I was going to compile it first, and then I was going to do the default none. Because how do you know which data attribute sharing clause pass here? You need to check all your variables, you need to do everything. The compiler can do it for you. So all we need to do here, I often say that the teacher who taught me OpenMP and who was also part of the OpenMP language committee, told me that having the shared by default was one of his deepest regrets in the OpenMP design. It should have been none, because then you know exactly what's happening. So let's make him proud. So my thread ID, how do you pass that? Who says shared? No, private. First private. Okay, private and first private both work, but look at what we're going to do with thread ID. Oh, we're going to have to initialize it. Yeah, of course. So I'm going to pass it as private. First private works equally well, okay, from a correctness point of view. Why? Because the first thing we're going to do inside is that we're going to set it equal something. So if you have an initialized value, it won't last long because you're going to overwrite it right away. Which value should I put in this, by the way? How do I get my thread ID? Yes. Okay, one less thing to worry about. So that's my thread ID. There's also something called start. That's tricky. Shared, private, first private. Okay, we had one person raising a hand discreetly this time. Okay, this one seems far less easy, it seems. Okay. We write into start, and it's used only by one thread. So in this case, anything works. If it's shared, it's not a problem, because it's only used by one thread anyway. So there will not be any interactions between threads. You're good. If it's private, so that master thread has a copy uninitialized, it doesn't matter, because you write into it first thing. If it's first private, copy but initialized, it doesn't matter because you overwrite it right away anyway. So everything works, but you have to give one explicitly. Okay, let's use private. Let's make it nice. Up. I already have a private here, so I can put it there. Let's see if I've got something. Nope, okay. Num threads equals 4. Good. So I have the master thread who ran the master block, and then another thread which is not the master thread, because the master thread is busy for 1 full second. So if in your code it's the same thread that did both codes, unless you have used explicitly one thread, something went wrong. Okay? Now, let's move to my favorite part in this whole presentation. When the remote wakes up. Okay. The synchronization constructs. So, let's consider this simple scenario. You have the slide, so you can go straight to the Fortran version if you want. I'm just asking all my threads to increment a shared variable. Okay, so a very, very, very simple way to calculate the number of threads manually, if you want, okay? What's gonna happen here? If I have 4 threads, okay, 4 threads, what will be the value of total thread count? What will be the value of thread count at the end? Who says 4? No one? I have 4 threads, each adding 1 to a value that is 0. So what value do you think would be in it? You will answer last. You know way too much on the topic. Yes. You say 4? Okay, who else says 4? Oh, yours seems so doubtful. You know there's something coming. That's right. So if it's not 4, what do you think it can be? Yes, go ahead. Yes, that's correct. for two reasons. Number one, each thread is going to increment this variable. So far, so good. One thread, we don't know which one, is going to print that statement, okay? But if the threads are operating in the following pattern, I'm thread 0, and I increment the variable. And I happen to call the print statement before the other 3 threads had time to reach line 4 and to increment the variable. I'm the only one who incremented that variable. So it means the other threads have not incremented yet, so if I print the value, it will show 1. If all the threads had time to call that increment, then the value has been incremented 4 times, so if I print the value, I print 4. And any scenario in between. So it can be 1, 2, 3, 4. But let's assume it's not even the problem, okay? Let's assume that by the time the thread that prints the statement, this is called after all 4 threads had time to call thread count plus plus. Who thinks it's 4 now? No one. Okay. If it's not 4, who thinks it's, I don't know, something else? Well, if it's not 4, it's something else. So far, so good. Do you have an idea of what it could be if it's not 4? Or are you just getting increasingly confused about something? You know it's coming, but you don't know what exactly. That's it. Okay. What we expect in our head is when we have 2 threads incrementing the same variable, I'm thread 0, so I'm going to get this variable from the RAM. I'm going to take it locally, increment it, and put it back. Another thread will then take it, go there, locally increment it, and put it back. That's perfectly reasonable. But we're now in parallel programming, which means things may happen with a different timing, such as this one. So if both threads get the value at the same time and locally add 1 on their side and try to bring it back, I'm thread 0, I see it's 0, I set it to 1, I put it back. The other thread read the value when it was still 0, so it took it away, added 1, brought it back. And now what we see is 1 plus 1 equals 1. In other words, and that's my favorite sentence in the whole teaching, you don't know how to add 2 numbers in parallel programming yet. Welcome in the game. When I discovered I couldn't even add 2 numbers, I was like, okay, that's really a whole world. It's a whole different thing. Yes, now what happens, this simple scenario is exactly what will trigger the hardest problems in parallel programming. It's when there's an extremely unlikely timing of events in an extremely complex problem and architecture. The one timing you never saw coming that happened and just crashes your whole application because now you have a very nasty thing that happened somewhere and propagated. Seems simple. Now imagine 200,000 lines of code or 1 million. Imagine what could happen. So to prevent this, let's move on. We're going to see 2 constructs, a few more constructs. Barrier and critical. So barrier is what we call a standalone directive. What does it mean? Is that there is no associated structure code. So there's no curly brackets in C. You just write this pragma and move on. There's no code attached to it like parallel or so on. When a thread reaches barrier, it will stay there until all the threads have reached it. And all the threads will resume execution only after all the threads reached that barrier. Simple, okay? So this is how you use it. You have your barrier, and there's no curly brackets below the barrier. The same way in OpenMP, in Fortran, there's no OMP end barrier. It's just barrier. Now, another one, which is easy to confuse with barrier or single, but it's something totally different. It's called critical. So critical is not a standalone directive, so this one you've seen so far with curly brackets and everything. And this one says, I want every thread to execute this code, okay? But one at a time. I don't want two threads to be able to do that piece of code at the same time. So our problem with thread count plus plus, for example, fixed. Because we cannot have two threads reading at the same time or something. They will do it one at a time. Okay? So this is how you do it. Pragma OMP critical or MP critical, your code inside, and that's it. The how this is done behind the scenes, that's the beauty of OpenMP. You don't have to worry about it. You're just guaranteed it will happen the way you want it to happen. Now, because I like also to give confusing details, you can name those constructs, okay? I'm just giving a name to it. Constructs, the critical constructs, because you can have more than one in your code, the ones that have the same name are mutually exclusive. So it means that a construct here and a construct there both will have every thread going through it, okay? One at a time, but we will not have a thread at the same time here and there. Okay, it will be at most one thread here or there, never at the same time in both. If you don't give a name, by default, a name is assigned for you to some random value you don't know, and you cannot know actually. So it means that by default, all your critical constructs are mutually exclusive. Now, if you want to see an example, to name a construct, a critical construct, you just need to pass the name between parentheses. That's all it takes, okay? You don't have to, but you can, if you want to do some subtlety in parallelism here. So the first critical and the last critical have the same name, so they're mutually exclusive with each other. So you cannot have a line, you cannot have a thread executing the code in the third critical while you have another thread executing the code in the first critical. That is just not possible. Each thread will still do it, and one at a time, but in one of these two sections. So you can really start to structure your parallelism, okay? It seems a bit less easy than it was at first, right? In the first hour. Yes. Yes, question? Yes. The one in the middle, critical B, you can have a thread executing that code at line 9 for the C version, while you also have a thread executing the code in the first or third critical construct. They can coexist, if you want, because they don't have the same name, so they're not mutually exclusive. Yes? Yes, the synchronization that is happening behind the scenes to make sure there's not more than one thread doing it means that you're going to have an overhead, a synchronization overhead. That means your performance will be indeed impacted by this. Did I answer the question? Oh, no, that's right. I was afraid I had gone a bit off topic. No. Yeah. But remember, in HPC, remember that one rule. Because you may be thinking, oh yeah, but that sucks. Because that just destroys performance. We're here to get high performance stuff. We're here first to get something that works and gives the right result. Once it works, you make it as fast as you want, sure. But if you make something super fast that doesn't give me the right result, I'll never use it. So if getting the right result implies to use critical, then you may optimize it and try to use very smart algorithmic techniques to even remove the need for critical. Okay, but first, you cannot say, I don't want to use critical, it's going to take time. Yeah, but you need to protect it. So, time for you to have fun with it if you don't have questions then. And after that, we dive into loops, which is where all the fun lies. Getting even better. Because what I meant implicitly was I want only one print. But I realized I don't say it here. But what's nice is you spot two things. You spotted that if you keep it inside the parallel region, you're going to have many of them. Then you thought probably what makes more sense is to have one of them. So you created the problem, and you also designed the solution. You said, I can use single, right? You're absolutely right. And then you have it. Do you have another way? You can use single, that's entirely correct. Do you have another way to have only one thread do something? That's correct. You have another way. Let me rephrase. Do you have another directive that can allow you to have only one thread doing it? We've seen single, and we've seen another one. That's the one. So you can even use master or single, and you're right. You can also not use any of this and use the thread ID. It might be very tempting to manually use the thread ID to say, oh, I'll just have one thread to do it. Yeah, but now think of something. If you know exactly which thread you would like to process this, it's fine, because you'll just say, if my thread ID equals 49, then I do this. And that will be correct. Now the issue is, what if thread 49 is the one that is super busy because it has a lot of work, and thread 48 has been waiting for the last half hour because there's nothing to do? That's much trickier to do manually. If you do OpenMP single, OpenMP behind the scenes will do all this monitoring for you, and as soon as there's one thread available, it will be the one taking it. So it can make your life easier. I guess we have 30 more seconds for the exercise. You may be wondering why I'm giving you exercises that seem so simple. I know that these ones now start to seem a bit more challenging, but it's like one statement and I just put two pragmas and that's it. Because I have more or less two ways to design exercises for this workshop. I can either give you exercises that are quite real world, so taking an actual piece of code and making you parallelize it. The issue is, it would require you to do a lot of thinking about how everything combines, which means I can cover only few directives. The choice I made was to cover many directives, which means only one exercise per technique, so it can illustrate in turn, in isolation, every technique or principle. The consequence of this is, when you leave that session, you don't know 2 or 3 directives, you know maybe 10. And the change is, when you get back to your department in computational chemistry, in astrophysics, in computer science, anywhere, you are aware of certain techniques that do exist. Maybe you don't remember the details, but you do remember there's this thing about synchronization or load balancing we're going to see, or parallelization, so you can get back online. Compared to knowing 2 directives really well, but you have no idea, there's even something called work sharing with single and master, it's going to be much harder for you to find this randomly online, okay? So I'm just giving you more tools, even if I don't give you a lot of experience with a lot of these tools, because the experience is what you will have in your work. You'll have a lot of experience. Finding new tools is a different type of difficulty. Okay, let's go for the questions when we fix this. So, first thing first, before I do anything about thread count plus plus and whatever, what do I do here at the end of parallel? What should I do? Yeah, let's make my teacher proud. I should totally send him the video. So what would you like to use for thread count? Do you use shared, private, first private? Who says shared? Okay, who says private? Okay. Private, okay. Who says first private? Or first private, okay. Here we need shared. Why? Because we want all threads incrementing the very same variable. If it's private or first private, they will have copies. So we'll never have the total. So shared. Now, how do we make sure that all threads had time to call thread ++ before we call printf? How do we make sure that all threads have reached that point before we can go further? Yes? So where do you put your critical construct? What do you put in it? What line do you put in it? 32 or 34 or both or something? Okay, so that's not the problem I was asking for, but you definitely found the problem that came right after, and you give the right answer. So you're even faster, that's why. So what happens is, you remember indeed that multiple threads may interfere with each other when they're trying to increment. So by using construct, you're addressing the issue. That's great. So let's do this. Pragma Okay. I'm gonna manage. Never give up in life. So Pragma OMP critical. Okay. There's also a typo on what, sorry? On line 30. Pragma OMP parallel default non-shared. Okay, thank you. Normally that's where I use all my bad faith and say it was made on purpose just to see if you would spot it. But the thing is, I've done way too many teachings online now. There are too many videos of me saying every time, yeah, it was made on purpose. So please don't check the other videos. So let's put this one in. Okay, so that makes sure that every thread will have time to do the increment and not be interrupted by another thread. Great. Now, how do I make sure that every thread had the chance to call this increment before doing the print? Yes. Exactly. So I insert the barrier here. Pragma OMP barrier. Okay. Now if I run this code, it's correct. The only problem is the printf is executed by all threads by reflex. So we can use single to make it run only on one thread. Which one? I don't really mind, just one. Fine. Good. If you run it, because you may think, oh, this to get the right result. If you run it with 256 threads, so you don't pass any OMP num threads value here, without all the fixes we've made, you will see what type of number you end up with. Actually, if I do it, check out. Okay, let's recompile. Let's run. So we have, oh yeah. Well, it seems that we don't have the same number of threads depending on who's saying it. That's number one problem, okay? But if I just do a single to make sure we only have one print, Pragma OMP single. So I have 13 threads. Religious people will be very happy to hear that their node have 13 threads. I have 13 threads again. 13 threads again. Okay, I'm totally disappointed. I was expecting a different number right now. But okay. The timing seems to be pretty consistent, and I still get 13. Okay, one more, just put. Ah! Okay, I give up after this one. Oh. No, it's okay. It's a global conspiracy or something. So now, actually, without really knowing, it may seem easy, it may seem maybe even boring because we're really taking our time, but you've seen already rather complex concepts, especially when they start to combine, right? So now that you've taken care of the general parallelism principles, let's dive into where most of your time is going to be spent, loops. Okay, if you have ever profiled a program, it's likely that most of your time is in a loop somewhere. So if you know how to parallelize loops, then you're going to get nice improvements in your performance. So if we take a classic loop, right, C and Fortran, I already showed you how to parallelize by injecting the parallelism spawning threads. So we just have to do it, and we should have that. So if we assume 4 threads, by doing this, that's what we expect, right? It's what we asked for. Each thread is going to pick 2 iterations, and we will have all 8 iterations done in parallel. Sounds good? Who thinks it's what's going to happen? Despite seeing me with a big smile. It's not going to happen. What we effectively asked here is this. So because if you do that after leaving this workshop, and you see that you have absolutely no performance improvement, and you start saying online, yeah, this teacher is absolute, it's a scam, it doesn't work. It's because what you asked was for every thread to run the entire for loop. What you want to do requires a new construct, one more word, for or do, depending on C or Fortran. In Fortran, you have do loops, so it's do. In C, we have for loops, so it's for. Okay. That now is going to tell all the threads, up. Before we start the for loop or the do loop, let's coordinate, because I want all these iterations to be split among us. So which iterations are going to take 0 and 1? Okay, I'll take 2 and 3, you take 3, 4. Okay. And that's where the split happens. Okay? Something that drives me crazy, but such is life. You cannot have curly brackets after the Pragma OMP4. You have to chain right away with a for loop. Why? I don't know. Maybe it's part of the Lexer, for those who know compiler. I don't know. The parser, maybe. Anyway. And there you get what you are looking for. Okay? The OpenMP people thought that Pragma OMP parallel, Pragma OMP4, that's 6 words. That's a lot of work. So we thought we can break it down by merging both into Pragma OMP parallel 4. So if you have a super, what we call embarrassingly parallel, so a for loop where all the iterations are independent, okay, and it's a serial program, you can just come to the department there, drop that line, compile and run, and see you made the program 10 times faster maybe just by using 10 threads in one line, and then say, hey, I'm HPC, I know. So it's really where most people get the most benefit from OpenMP. You just drop that one magic line. I'll show you one more magic line for GPUs tomorrow, the one you drop and then you move on with your life. OpenMP is really designed for this. You have a question, I think. Yep. Did you have a question? Yes. Yes. Oh, yes. When I say independent, it means that, yeah, the execution of an iteration does not depend on the execution of other iterations. There's no cross-iteration dependency, as we say. To calculate to calculate the iteration 8, you don't need to have done iteration 7. If you haven't done iteration 7, it will not change anything you're doing in iteration 8, which might be different if it was AI equals AI minus 1 plus something. Now you need to have A minus 1 updated. So that would be a different situation. So, parallelizing loops that don't have this iteration independence is way trickier. It can be done in certain contexts with certain techniques and certain algorithmic situations, but it's instantly much harder. much, much harder. And sometimes just impossible, by definition. So now that you're ready to conquer the world, we have that case. Let's see. I think it's actually what you have to do in the for loop. Let me check the exercise. I don't know if I have a comment to make right here or if it's just after. I would like to check. I'll make this later. Okay, so then time for you to have fun with the for do. Same thing, 6-7 minutes on your own. If you have any questions, ask, and then we move on step by step together. Go ahead. No worries. Yes. Default none is to make sure. Did you say, why do I say that we should use default none? It's because if you don't use default none, your variables will go through with an implicitly applied data sharing attribute by default. In other words, on CPUs, all your variables will be passed as shared. If it's what you were expecting, good. If you meant to send them as private, not good. If it's my thread ID, we set, by default, it will be passed as shared. So every thread is going to overwrite the value of the other thread. So if you mean to have that as a copy, you need to make sure it was passed as a copy. And to easily spot places where you haven't said explicitly how a variable was passed, using default none helps you spot it, because the compiler will say, hey, my thread ID, I was about to pass it as shared by Reflex, but you said you need to tell me explicitly how to pass it, and you haven't, so I will not compile.